In 10.7, we're going to look at our last two tests for convergence. Yay! So this would be the ratio and the root tests. They're really nice tests, and they can be used with any series, geometric, telescoping, alternating series, and so on. However, what I'd like to do first is just review what a factorial is. This comes up a lot when you're looking at the ratio test. So factorials can be expanded out. For example, 5 factorial is 5 times 4 times 3 times 2 times 1. Now, if you just look at the 4 times 3 times 2 times 1, that's 4 factorial. So I can rewrite 5 factorial as 5 times 4 factorial. Oops, sorry. And that's going to help us when we look at the ratio tests and our series has a factorial in it. So the ratio test says that what we're going to do is we're going to compute the limit of the absolute value of the k plus 1 term over the k term. And that's why it's called a ratio test, because you're computing the limit of the ratio. Now this variable r really doesn't matter. The only reason why r is there is so that we can easily define our 3 conditions for the ratio test. However, what you should notice is that there's an absolute value there. Going back to our previous section, remember that if the absolute value of a series converges, then the series converges absolutely. And that's what we're using here. If we take the limit of the absolute value of the k plus 1 over the k term, and if that converges, then the series converges absolutely. So it doesn't really matter if it's an alternating series or not. Once you take that limit, you're going to have the 3 conditions. So if it turns out that the limit is less than 1, then the series will converge absolutely, which just means it converges. If the limit is greater than 1, and here we're including infinity, then our series will diverge. If it's equal to 1, the test is inconclusive. So inconclusive does not mean it diverges. It means that you need to do something else. Try another test. Let's look at example 1. We want to determine whether the series converges. So if we look at 1a, we would be taking the limit as k goes to infinity of the absolute value of -1. So now it's the k plus 1 term. So wherever I see k, I'm just going to substitute in k plus 1. So -1 to the k plus 1 times 5 to the k plus 1 divided by k plus 1 in parentheses factorial. And this is going to be all over the k term, which is going to be -1 to the k, 5 to the k, divided by k factorial, all inside the absolute values. Something you should notice is that the -1 to the k plus 1, the absolute value of that is just 1. So I can get rid of that. And the -1 to the k in the denominator, absolute value is just 1. So it's gone. And now what remains does not need absolute values on it because your k values are positive. These are all positive values. So this would be equal to the limit as k goes to infinity of 5 to the k plus 1 divided by k plus 1 factorial over 5 to the k divided by k factorial. And this is actually where you can start. Whenever you have an alternating series, you can assume that the -1 to whatever power it is, that's going to cancel out. So you can always just start here. You don't have to start with the absolute value. Well, let's look at this. If k goes to infinity, I have a lot of infinities over infinity over infinity over infinity. This is just ridiculous. So I'm going to algebraically rewrite this. Get rid of the complex fraction by taking the numerator divided by the reciprocal of the denominator to get 5 to the k plus 1 over k plus 1 factorial times reciprocal would be k factorial over 5k. So nothing cancels. However, notice that 5 to the k plus 1 is actually 5 to the k times 5. And k factorial, if I expand it out, would be k plus 1 times k factorial. And now I can see that the 5k's cancel and the k factorials cancel. And I'm just looking at the limit as k goes to infinity of 5 over k plus 1. And that would be 0. So by the condition, it meets condition 1. The limit is less than 1. So this converges by ratio test. Typically, if you see a factorial, and this is not always true, but 99% of the time, if you see a factorial in your expression, in your series, then the ratio test is nice because you can you can expand out the factorial and cancel. Let's look at example B. We have a series 7k over k to the 50. Notice that there's no negative in there. For the k values, this expression is always positive. So the absolute values are really not needed. And I can go straight to evaluating the limit as k goes to infinity of 7 to the k plus 1 over k plus 1 to the 50th power over 7 to the k divided by k to the 50. And then I'm going to rewrite that as 7 to the k plus 1, so that becomes 7 to the k times 7 divided by k plus 1 to the 50 times k to the 50 over 7 to the k. So notice that the 7 to the k cancels in the numerator and denominator. Now if I were to evaluate this limit as k goes to infinity, I have infinity over infinity, which is an indeterminate form. I don't really want to do L'Hopital's because look at the exponent 50, that's crazy. It's not really going to help me in any way, or maybe it will. Maybe I could do L'Hopital's and something will cancel. But instead, what I'm going to do is, and also notice that I can factor out this 7 in the numerator because that's just a constant. What I'm going to instead do is notice that both of these expressions k and k plus 1 have the same exponent. So algebraically, I can write them as k over k plus 1 to the 50th power. I can combine them. Now I still get infinity over infinity inside the parentheses, but what I can do now is divide the terms, top and bottom, by k to get 1 over 1 plus 1 over k to the 50th power. And now when I take the limit as k goes to infinity, the 1 over k goes to 0. So this limit is going to be 1 to the 50th power, which is just 1. And then 7 is greater than 1. So by the second criteria, the series is going to diverge. So my conclusion is diverges by ratio test. Let's move on to the root test. With the root test, the conditions are all the same, different variables, and that's just because we used r in the ratio test. So now the symbol we're using is the Greek symbol rho for root. Again, it doesn't really matter. The only reason why that's there is so that we can easily define the three conditions. So in the root test, we take the kth root of the absolute value of the series. The advantage to using the root test is that when you have an expression to the kth power, the root and the exponent cancel. So again, all the conditions were the same. Less than 1, greater than 1, equal to 1 is inconclusive. Just remember, inconclusive means try something else. So if I were to take the limit as k goes to infinity of the kth root of the absolute value of 5 to the k over k to the 27, something to notice is that I don't need the absolute values, so I could actually have started here. Again, I don't need the absolute values because 5 to the k over k to the 27 is always positive, so I can just drop them. And I have the kth root of 5 to the k over k to the 27. So notice in the numerator, the 5 to the k and the kth root, they're going to cancel, but not in the denominator. So this becomes 5 in the numerator because the k exponent and the kth root cancel. And the denominator is going to still be the kth root of k to the 27. All right, so I have an issue. As k goes to infinity, I get an indeterminate form in the denominator. Oh, here, why don't I just bring out the 5? And I'm going to write this as k to the 1 over k to the 27 power, just so it's easier to see. So notice as k goes to infinity, this is actually 1 over infinity to the 0 power. And infinity to the 0 power is indeterminate. That tells me that I need to do something more. So what I can do is just take the limit. I'm going to do this off to the side. I'm just going to look at the limit as k goes to infinity of k to the 1 over k. So the problem with this indeterminate form is that I have k in the base and k is in the exponent. So we're going to go back to the strategy of taking e to the ln of our expression, which means I can just look at that natural log of k to the 1 over k, and that becomes 1 over k natural log of k. Remember, the advantage to doing that natural log is to get that exponent into the front of the expression. When we look at the limit, as k goes to infinity of 1 over k natural log of k, the 1 over k is going to be 0. Natural log of k as k goes to infinity is infinity. It's an indeterminate form, which means we're going to rewrite this as natural log of k over k. And now we get infinity over infinity, which means I can use L'Hopital's to take the derivative of the numerator. So that's 1 over k. The derivative of the denominator is just 1. So this becomes the limit as k goes to infinity of 1 over k. And that's 0. But remember, that's the exponent on e, which is equal to 1. That does not mean the test is inconclusive, because remember that this 1 is the limit of k to the 1 over k power. So this limit is 5 times 1 over 1 to the 27 is 1. It's 5, which is greater than 1. And we have diverges by root test. All right, let's do some more examples. Example B, we have k plus 2 over k to the k squared. So notice that if I take the absolute value of this series, it's going to remain the same. So I really don't need the absolute values when I look at the limit. Something I would like to do though is look at that k squared exponent, because that will not cancel when I take the kth root, because it's not just k, it's k squared. So this is actually k plus 2 over k to the k power, all raised to the k power. So now when I take the kth root, that outside exponent k will cancel. So let's look at the limit. Again, we don't need the absolute values. As k goes to infinity, of the kth root of, let's see if I make this big enough, k plus 2 over k to the k power, all to the k power. And then I can see that the root and the outside exponent k will cancel. This becomes the limit as k goes to infinity of k plus 2 over k to the k power. Unfortunately, that's infinity over infinity to the infinity, and the infinity over infinity is an indeterminate form. What I do notice is that I have a single term k in the denominator, so I could break this up as 1 plus 2 over k to the k power. And now when I take the limit as k goes to infinity, 2 over k goes to 0. So this is 1 to the infinity power, which unfortunately is an indeterminate form, but it's of the form, it's of the form where I can do what I did previously. I can look at the e to the ln. So the 1 plus 2 over k to the k is going to be e to the ln of that whole expression, which would be e to the k times the natural log of 1 plus 2 over k. And then I can go ahead and just look at the limit as k goes to infinity of k times the natural log of 1 plus 2 over k. So that limit is going to be infinity times, as k goes to infinity, 2 over k goes to 0, natural log of 1 is 0. Indeterminate form, but it tells me that I could rewrite this as a fraction by dropping the k into the denominator as 1 over k. Now when I take the limit as k goes to infinity, this is simply infinity, sorry, I lied. This is simply 0 over 0, and I can use L'Hopital's. So by L'Hopital's, I would take the derivative of the top and the bottom. Sorry, that's limit. And this is supposed to be natural log. Can't write. So the derivative of natural log is 1 over the argument. So this is 1 over 1 plus 2 over k times the derivative with respect to k. And I'm not going to compute it because something nice will happen. 1 plus 2 over k, and then I take the derivative with respect to k of 1 over k. So the reason why I didn't compute the derivative is because I noticed that if I take the derivative, cannot talk and write today, if I take the derivative with respect to k, the derivative of 1 is simply 0. So now I'm just looking at the derivative of 2 over k, and notice this 2 is just a constant that I could bring out. The derivative of 1 over k is the same as the derivative of 1 over k in the denominator. So if I bring this 2 out, these derivatives cancel. And this becomes the limit as k goes to infinity of 1 over 1 plus 2 over k times 2. And I can also bring that 2 out into the front. and write 2 times the limit as k goes to infinity of 1 over 1 plus 2 over k. It's a lot. Now when I take the limit as k goes to infinity, the 2 over k is going to go to 0. And this is just 2 times 1, which is 2. But remember, that was the exponent on e. Going back to our limit, this is the limit of e squared, which is greater than 1. So we have diverges by the root test. All right, so we're just going to look at one more example. It's a very short section. In part C, I see the kth root and the exponent k will cancel nicely, but I do have to be careful with this absolute value. I can't just write it without absolute values because notice in the numerator, did the absolute value of, or actually just let's look at 1 minus 2k. Remember, k is always positive. So this is actually going to be negative. I need the absolute values on this. So I'm going to look at the kth root of the absolute value of 1 minus 2k over 5k plus 7 to the kth power. Close my absolute values. Since my k, my exponent k here, that's always a positive exponent, I can actually bring it out of the absolute value, and then the root and the exponent k will cancel, but the absolute values do not cancel. This is the limit as k goes to infinity of the absolute value of 1 minus 2k over 5k plus 7 in the absolute values. So if I were to evaluate this limit, I'm getting negative infinity over infinity. It's an indeterminate form. So one thing I could do is try to get rid of the absolute values and see if something nice happens. Well, let's go back to the definition of absolute value from algebra. Whenever you have an absolute value, you're just making whatever it is positive if it's negative. However, if what's inside the absolute value is already positive or 0, you just drop your absolute values. If what's inside the absolute value is negative, if you take the negative of a negative, you get a positive. So if what's inside the absolute values is negative, you take its negative. The absolute value of 1 minus 2k, that's going to be equal to the negative of 1 minus 2k, which is simply negative 1 plus 2k. Or you could just rearrange it as 2k minus 1. If you take the absolute value of a subtraction where you have two terms, really all you're doing is flipping the terms. So I can get rid of the absolute values. This becomes the limit as k goes to infinity of 2k minus 1. Over the 5k plus 7, I had no issue with that. That's always positive. So I just dropped the absolute values. Now this is infinity over infinity. I could divide all the terms by k, or I could just use L'Hopital's, which is what I'm going to do. I'm going to take the derivative in the numerator, so that's just 2, and the denominator would be 5. So notice my limit here is 2/5, which is less than 1. So this converges by the root test. We didn't do any examples where it was inconclusive, but if you do get inconclusive, then all you would have to do is just try another test. And we had a bunch of tests. So what you would first do is look to see if it's a geometric or a telescoping series, because then you don't have to do any of those tests. They have special conditions. If not, try the divergence test. That doesn't work. Then look at integral comparison or limit comparison and see if those work. If none of those work, then you can't determine whether the series converges or diverges. And sometimes that happens where it's just not possible. And that's it for this section.